Okay, we have another problem from Morin. This one is similar to the one previously, where we're now adding in an extra force, not just gravity, but we're going to add in a wind force. This time, however, let's look at level ground. We're not throwing off of a cliff. And imagine that the wind force blows to the right. So we're now throwing with a tailwind. And the question is, what angle maximizes the range of this projectile under these conditions, and maybe also what is that maximal range. Again, we will assume that the wind force is a constant that is equal to the weight of the projectile. Maybe in a future video, I'll generalize this to a generic wind force, or maybe this is a generic horizontal wind force, and we'll see what happens. But right now we want to know, what is this maximal range? What angle maximizes that? Okay, so as before, we now have to go back to our original kinematics equations and modify them. At least the wind force is still constant, so that means that our acceleration is constant, which means we can still use our constant acceleration kinematics equations as a starting point. So let's start with that. I'm going to go ahead and once again assume that we're launching from the origin. And what I'm really interested in here, of course, is the range. I want to know, where does y equal 0 the second time? What x position gives me that? So I'm going to try to solve for the range r. And I know that this was a launch of 0. We now are launching at some generic angle, theta. So that'll be a v0 cosine t, cosine theta. And then the time of flight we'll call capital T. This time, again, however, ax is not equal to 0 because we do have this acceleration from the wind in the horizontal direction. And because it's equal to mg, the acceleration will be g, but it'll be positive. That t is our capital T. Okay. In the y direction, it has the usual flavor. We're going to end on the ground, and we're starting on the ground. We do have a y component of our initial velocity, and the acceleration is still minus g in the y direction. No change there. So from this equation, we can quickly solve for the flight time. It's actually the same as what we've had throughout all these problems. There's no change there because we've only changed the force in the x direction, not the y direction. So the flight time is the same. Now we can sub that back in for our range equation. And we get that the range is v0 cosine theta times 2 v0 sine theta over g. This bit, maybe simplified a bit, would be the range in the absence of any wind. So we've seen that before. But now we have this new term. We've got a g and then this squared. Okay, let's go ahead and try to clean up some of this with some algebra and trigonometry. So I'm going to factor out whatever I can. Notice that there's a v0 squared in both terms. There's a 1 over g in both terms after this cancels the g squared. There's a 2 in both terms because this 2 squared cancels the 1/2 out front. So all of that comes out to the front. Then I've got sine theta, cosine theta. I'm not going to use any double angle formulas here. Let's leave it as is. And then we'll also have a sine squared theta. Okay, so this is our range formula generically now. The first term was the original. This second piece is what comes from the additional range given by the wind blowing you forward. Now we want to maximize this, so let's do some calculus. I'm going to set the theta derivative of this to 0. The stuff out front is a constant. And now I'm just going to use the product rule and chain rule to take a quick derivative here. Okay, so we end up with our derivatives here using the chain rule and the product rule. I am going to go ahead now and use a little bit of trigonometric identities to simplify this. Notice that 2 sine theta cosine theta is sine 2 theta. That's the double angle identity for sine. I also have cosine squared minus sine squared. That's the double angle identity for cosine. Okay, so what we really have here is 0 equals cos 2 theta plus sine 2 theta. Let's bring that back up to the top and we'll finish this off. Okay, I've rewritten our range equation generically up at the top. I put the 2 inside because we're going to do some stuff with it in a sec. And then here's the condition on our theta that maximizes the range. We found that cosine 2 theta plus sine 2 theta equals 0. Pretty easily that tells us that tan 2 theta star is minus 1. And so we ask, okay, what angle has a tangent of minus 1? That is, well, in the first 2 quadrants, let's say, because we'll divide by 2 in a sec, well, that'd be 3 pi over 4. So tangent of 3 pi over 4 is minus 1. That must mean that our magical angle is 3 pi over 8. So there's the answer to the question. This launch angle will maximize the range of our projectile when we include the wind. Notice that it is a little higher than pi over 4. Which would be the same thing as 2 pi over 8. So we are aiming a little bit up, basically to stay in the air longer and take advantage of that horizontal wind longer. Now let's actually find what this angle is. Now we could go plug this right back in and, I don't know, use a calculator or something, but let's practice our trigonometry. It's always a good thing to do that. I'm going to rewrite this a little bit with some more double angle formulas. And the reason why is 3 pi over 8 is not like a super nice angle. It's fine, but it's not nice like a pi over 4 type angle. So let's rewrite everything in terms of 2 thetas, because then I might get a 3 pi over 4, and I know those off the top of my head, right? So rewriting the range formula, we already know this first term is the double angle identity for theta. In fact, that first term is our usual range formula when there's no wind. This second term, though, may be a little trickier. I want to use the power reduction formula. So notice I have a sine squared. I want to turn that into something that involves just a single power, but maybe double the angle. And let's recall, maybe off to the side here, that sine squared x is the same thing as 1 minus cosine 2x all over 2. So that is, and that is the power reduction formula for sine. Notice that we do pick up a double angle that we're after. And the 2 right here will cancel the 2 right there, so it's already kind of not so bad. And now we see that we have a sine 2 theta minus cosine 2 theta. Can't really simplify that, but we know what 2 theta is more easily. We do end up with this extra plus 1. And so our star, which is our maximal range when we launch at that particular angle, sine of 2 theta is going to be the sine of 3 pi over 4. Okay, sine of 3 pi over 4 is in quadrant 2, so we know sine is positive there, and we know that its value is 1 over root 2. We've got a plus 1. And then we have minus the cosine of 2 theta. Okay, cosine of 3 pi over 4. Again, we're in quadrant 2. Cosine is negative there. So I'll be subtracting negative 1 over root 2. 1 over root 2 minus 1 over root 2 is 2 over root 2, which we also call root 2. So there's the 1 left over, and then there is a root 2. So notice that the 1 by itself was the original max range, but we get this extra bit. We actually more than double this max range by including the force of the wind. And we end up with this range being maximized at a steeper angle and quite a bit farther distance. QED.